Alright, in this video, we first define the natural logarithm. Then as the inverse function of this, we define exponential function from real to real. Then we show that this is indeed can be written as exponential of some constant e. Then extend this function to complex domain, to complex codomain. Okay, let's start. Although we will study calculus in detail in other videos, I assume that you already know some calculus. So we define the natural logarithm function log from 0 to infinity to real numbers. So its domain is this interval from 0 to infinity, not including 0 itself. And we define this function by this. It's based on integral from 1 to x of 1 over t dt. Okay, so 1 over t looks like this. We only consider positive part, right? And we integrate this from 1 to x. So let's say this is 1. Then when t is 1, then 1 over t is 1. And when x is greater than 1, then this integral means the area under the curve between 1 and x. Okay? When x is less than 1, that's right. Then what happens? So since x is less than 1, in that case, we swap the sign of this function. So it will be, let's say, if x is somewhere here, it will be the negative of this area, this red region. Okay. Of course, when x is 1, it's 0 because it's integrating from 1 to 1. So the area under the curve is just this line. So the area is 0. So let's see the properties of this function. First of all, as I already explained, log of 1 is 0. It's obvious from the definition. And 2, this function is strictly increasing function. Okay, it's strictly increasing. So what this means is the following. That means if x1 is less than x2, then log of x1 is also less than log of x2. Okay. So actually, if you plot this function, it looks like this. X is here, and log of x, if you plot it, then it looks like something like this. Okay, so when x is 1, it's 0. And when x is less than 1, it's negative. And as x approaches 0, it diverges to negative infinity. And when x goes to infinity, log of x diverges to infinity. And if x1 is less than x2, then the value of log of x1 is less than log of x2. And also, this is a continuous function. So continuous function means this. If we take the limit of log of x and x approaches a, then the result is always log of a. Okay, so if a is here, and if we move x towards a from either from right or left, then the value of log of x approaches log of a. Okay, so it's continuous everywhere on the domain. Okay, next let's prove this important property of the logarithm. Log of y1 times y2 is equal to the sum of log y1 and log y2. And of course, we're assuming both y1 and y2 are positive real numbers. Okay? So this says the log of a product is the sum of the logs. So product becomes sum, okay, for the log function. Okay, so let's prove this. By definition, log of y1, y2 is equal to this integral from 1 to y1 times y2 of this function. Okay, then we split this integral into two pieces, from 1 to y1 and y1 to y1 times y2. So what we are doing is this. By definition of the log, it's the area under the curve between y1 and y2. So this area. So that's this integral. Now, if y1 is here, then we split this area into two pieces, this and this. So this corresponds to the first integral, and this corresponds to the second integral. And the first integral is, by definition, it's log of y1. And the second integral, let's change the variables. So multiply both numerator and denominator by y1. And change the variables from t to s by this change of variable. y1 times t is equal to s. Okay, so when t is equal to y1, then s is equal to 1. When t is equal to y1 times y2, then s is equal to s is equal to, so y1 times y2 divided by y1 is y2, right? And ds is equal to y1 dt. So this one becomes ds, and this one becomes s, and this one becomes 1, and this one becomes y2. So this integral becomes ds over s. So this is, by definition, is equal to log of y2. So there we go. y1 plus log of y2, and we are done. Okay, as a corollary to this lemma, we have the following. Log of x to the power of n. Of course, x is positive real number, and n is a natural number. Okay. Then this is equal to n times log of x. Okay, you should try to prove this. For example, by using mathematical induction. Okay, the hint is x to the power of n is x times x to the power of n minus 1. Or if you continue this, this is just x times x times x times x n times. Okay? And yet another corollary is log of 1 over x is equal to negative log of x. Okay, so let's prove this. So by the property of log, log of 1 is equal to 0. But 1 can be written as x times 1 over x. Okay? But we have seen that the log of product is the sum of logs. So this is log of x plus log of 1 over x. So this is equal to 0. Therefore, we have log of 1 over x is equal to negative log of x. Okay, so from this equality, we can see that if x is greater than 1, then 1 over x is less than 1. And because of that, 1 over log of 1 over x is less than 0. And if x goes to infinity, then 1 over x converges to 0. And since it's a strictly increasing function of x, so if 1 over x becomes smaller and smaller and towards 0, then log of 1 over x becomes arbitrarily small. So it diverges to negative infinity. Okay, so that means this function, log of x, from 0 to infinity to real numbers, it's a surjective function. Okay, so for any real numbers, there is some x such that log of x is that real number. So let's write that. So for any real number, there exists some x between 0 and infinity such that log of x is equal to y. And also, so therefore log is surjective. And of course, since log is strictly increasing function, if x1 is not equal to x2, then log of x1 is not equal to log of x2. So therefore, log is also injective. Okay, so that means together we have log is bijective. It's a bijective function or bijection. So as we have seen before, if a function is bijective, then there exists its inverse. So let's call that inverse function inverse of log as exponential function. Okay. So graphically, if you plot the logarithm function, it looks like this. Okay. So it diverges to negative infinity as x goes to 0, and it diverges to positive infinity as x goes to positive infinity. So its inverse function is it can be drawn as the mirror image around this diagonal line. So the mirror image would be something like this, right? So here's 1. So the y-intercept is 1. And as x goes to negative infinity, this inverse function called exp, actually it's an exponential function, converges to 0. And as x goes to infinity, then this inverse function diverges to positive infinity, converges to 0, and diverges to positive infinity. So this inverse function exponential exp is a function from real numbers to positive real numbers. Now let's see some properties of this function, the inverse of log. First of all, it's easy to see that since log of 1 is 0, then because of this, exponential of 0 is 1, because it's inverse, right? And now we define a special constant, e, as exponential of 1. Okay, so this function, so let's see, y is equal to exp of x looks like this. So when x is equal to 0, it's 1. So when x is 1, then it has some value somewhat greater than 1, and that we call e. Okay, and we'll see that this is equal to 2.718 and so on, and it's an irrational number. And from now on, we prove that exp of x is actually equal to e to the power of x. But what we mean by this required some explanation. All right, so let's prove this property first. Exponential of a sum is the product of exponentials. Okay, so this is actually derives from the fact that the log of product, remember, is the sum of logs. Okay, so let's prove this. Let y1 be exponential of x1 and y2 be exponential of x2. So using this equality, we have log of y1, y2 is equal to log of y1 plus log of y2. So therefore, using this, we have x1 and x2. Okay, so this means log of y1 is equal to x1 and log of y2 is equal to x2, right? So we have this. So now, because of this, since exponential is the inverse of log, we have y1 times y2 is equal to exponential of this thing, x1 plus x2. However, y1 is this and y2 is this. Therefore, we have exponential of x1 times exponential of y2. Sorry, not y2, x2 is equal to exponential of x1 plus x2, and we are done. Okay, from this, in particular, we can see that exponential of 2 is equal to exponential of 1 plus 1. So that is exponential of 1 times exponential of 1. But we have defined that exponential of 1 is e, so it's a constant. So it's e times e, so therefore it is e to the power of 2. And you can continue this for exponential of 3. And you can see that this should be equal to exponential e to the power of 3. And more generally, for any natural number n, n is a natural number, this is equal to e to the power of n. So at least for natural numbers, now we have proved that exponential of n is equal to e to the power of n. Next, we are going to extend this relation to any integers, including negative integers. Okay, to begin with, we know that exponential of 0 is equal to 1. But 0 is equal to n minus n. And minus n is actually, so subtraction is actually addition of negative integer. And as we have seen before, this can be split into the product, exponential of n times exponential of negative n. And from this result, we know that this part, so for positive n, it's a to the power of n. Therefore, and this is equal to 1, so exponential of negative n is equal to 1 over e to the power of n, which is equal to e to the power of negative n. So we have negative n here and negative n here. So after all, we have, for any integers, let's see, for any integer z, we have exponential of z is equal to e to the power of z. And of course, when z is 0, this is 0, and this is e to the power of 0. So power to the 0 is always 1. So this is indeed true for any integers. Okay, next, we show that this relation holds in for all rational numbers, not just integers. Okay, so to begin with, first, let's see, e is equal to exponential of 1. And so this is by definition. And 1 is equal to n over n. Okay, here n is any natural number. Okay, and this is equal to 1 over n plus 1 over n plus and so on plus n. So this is the sum of n terms. And we know that the exponential of sum is the product of exponentials. So this is exponential of 1 over n times exponential of 1 over n times and so on times exponential of 1 over n and n terms. So the product of n factors. So this is exponential of 1 over n to the power of n, right? Because we're just multiplying the same factor n times. So this means, so this is equal to e. Therefore, exponential of 1 over n is equal to e to the power of, so it's nth root of e. So here we have 1 over n here, 1 over n, and 1 over n here. And next, consider any rational number, say m over n. Okay, and n is a natural number, and m is an integer. Okay, then exponential of m over n is exponential of 1 over n, everything to the power of m. So as we have seen before, this m can be either positive or negative. We still have this equality. But from here, we know this inside is e to the power of 1 over n. So this is equal to e to the power of m over n. So we have m over n, m over n. So that means this expression, let's say exponential of q is equal to e to the power of q, holds for any rational numbers. And finally, this function, exponential of x, is continuous. because to begin with, the log function was continuous, so its inverse should be also continuous. And any real number can be approximated by some rational numbers to arbitrary accuracy. So that means from the continuity of real numbers and continuity of this function, we have exponential of x is equal to e to the power of x for all real numbers. So we have this expression now. And next we show a very interesting property of this exponential function. That is, exponential function is a function such that when differentiated, it yields the same function. It stays the same. Okay? If you differentiate e to the power of x, then the result is e to the power of x. Okay, so let's show this. Okay, let y equal to exponential of x. So this is, of course, e to the power of x. Then the logarithmic function is its inverse. So we have x is equal to log of y. So if you differentiate both sides with respect to x, we have 1 on the left-hand side. And by the definition of this, it was like not 0. It's from 1. It's an integral from 1 to x, 1 over t dt. So if you differentiate this with respect to, actually it should be y here, with respect to y, then it yields 1 over y, right? 1 over y, and by the chain rule, we have dy dx here. So, as a result, we have dy dx is equal to y. But y is this. Y is, wait a minute, e to the power of x. So we have this. We are done. So now we have this exponential function defined on the real domain. We want to extend this function to the complex domain. Okay, so this exponential function is from real to real. Actually, the codomain is positive real numbers. But now we extend this to complex to complex. So how do we do that? And here's the definition. Okay, let a complex number z be u plus I theta, where u and theta are real. Okay, real part and imaginary part. Then we define e to the power of z as this. E to the power of u times cosine theta plus I sine theta. Don't get confused. We are now defining this left-hand side. And on the right-hand side, we have e to the power of u. But this is a function from real to positive reals. Okay? This function. It's already defined here. And this function is now being defined here. Okay? So we take the real part and take the exponential of that. And for the imaginary part, we take this, cosine theta plus I sine theta. Well, in mathematics in general, it's one thing to define anything in any way you want. But it's a whole totally different thing that definition works consistently or in a sensible manner. So let's see that this definition is okay with it can get along with the previous definition of the exponential function on the real domain. So there shouldn't be any contradiction between these two functions. So one way to show that this definition is consistent is to show that it behaves in a similar manner as the real function. Okay, so one way is this. So here's the lemma. If we have two complex numbers, z1 and z2, and an integer k, we have the following. 1, exponential of z1 times exponential of z2 is equal to exponential of z1 plus z2. So the exponential of the sum is the product of exponentials. So this also holds for the original exponential function for the real domain. And it also holds for the complex domain. So they behave in the same manner. And similarly, exponential of z to the power of k is equal to exponential of k times z1. Okay, z1, z1 here. So this is also the same behavior as the real function. So because of these properties, if the complex number happens to be purely real, there is no contradiction with the previous definition of the real functions. Okay, they behave indistinguishably. Okay, anyway, let's prove this. Okay, proof. So how do we prove this? First, let's say z1 is equal to u1 plus I theta 1, and z2 is equal to u2 plus I theta 2. So substitute these into the left-hand side. Then we have, so by definition, this part is e to the power of u1 times cosine theta 1 I sine theta 1 times this part, e to the power of u2 cosine theta 2 plus I sine theta 2. And so this is just multiplication. And because of the property of the real version of exponential function, we have e to the power of u1 plus u2 here. And here, remember, this is a complex number with absolute value of 1, and same for the second one. So that means they represent rotation by these angles, right? And if we multiply them, then we rotate by theta 1 plus theta 2. So, okay, alternatively, you can use the trigonometric identities. But anyway, the result should be cosine theta 1 plus theta 2. And I sine theta 1 plus theta 2. However, this is, by definition, equal to exponential of u1 plus uz plus I theta 1 plus theta 2. But this is equal to exponential of z1 plus z2, right? Because of this. So it's done. Okay, and the second part, I leave it as an exercise. So you should try to prove it. Okay, so anyway, let's see a few examples. And first of all, from the definition, we have this famous formula. It's Euler's formula. Okay, e to the power of I pi is equal to -1. Of course, I means the imaginary unit. Okay, let's see this more explicitly. So by definition, here the real part of this exponent is 0. Therefore, it's e to the power of 0 times cosine pi plus I sine pi. And cosine pi is -1. So this is 1. This is -1, and this is 0. Therefore, we have this equality. And more generally, any pure exponential function of any purely imaginary complex number can be written as cosine theta plus I sine theta, right? Because the real part is 0, so we don't have extra factor here. So because of this, the polar form of any complex number, so we have defined polar form as this, cosine. So we have seen any complex number may be written in this form. So this can be also written as r times e to the power of I theta. Okay, so this is a little bit simpler notation than previous polar form. So you can also use this as a polar form. It's the same thing. And actually using this polar form and the property of exponential function, it's actually easier to show the trigonometric identities. For example, if we have e to the power of alpha times e to the power of beta, then we have e to the power of I alpha plus beta. Okay. Now this is equal to cosine alpha plus beta and I sine alpha plus beta. And this one you can write as cosine alpha plus I sine alpha times cosine beta plus I sine beta. So if you expand this and compare the real part and the imaginary part, you can show that you can again show the trigonometric identities. That is cosine alpha plus beta. So just multiply all these factors and summarize the real part. Then you get cosine alpha, cosine beta, minus sine alpha, sine beta. And the imaginary part is sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha and sine beta. And also exponential of I theta is cosine theta plus I sine theta, and exponential of negative theta, I theta, is cosine theta minus I sine theta. Remember, cosine is an even function and sine is an odd function. So the negative sign here comes out of sine function, but it disappears for the cosine function. So if we add both sides of this, we have exponential of I theta plus exponential of I minus I theta equals to, so this and this, we have 2 cosine theta. Therefore, we can write cosine theta as this divided by 2. And if we subtract the second equation from the first equation, we can show that sine theta can be written as e to the power of I theta minus e to the power of negative I theta divided by 2I. So these are 2 alternative definitions for cosine and sine. Okay, that's all for this video. See you later.